Hey everyone, I'm Rokas. I'm here to present our work, Deprecating Benchmarks, Criteria and Framework. It's a joint collaboration, and here are my co-authors, Arten, Leon, and Ariel. I'll try to give a high-level overview of the paper first. It's about deprecating, or in other words, retiring benchmarks once they are no longer suitable for a particular task or context. So we are proposing an active deprecation to prevent distorted capability assessments, wasted resources, and safety washing. We differentiate between two levels of deprecation. It could either be complete or partial, and when I say partial, I mean that a particular component of a certain benchmark could be updated without retiring that benchmark completely. We think that the deprecation process could be carried out by governance actors, such as government agencies, certain AI safety and security institutes, or industry panels, and they could maintain curated deprecation lists for different usage contexts. New benchmarks are introduced each day, but the problem is that they vary in quality, so we might want to raise a question, which benchmarks should be used. However, this question is a bit problematic because different actors in the AI evaluation space, when answering this question, might lean towards cherry-picking certain benchmarks or selecting them just because of the research inertia, and this overall might lead to slow adoption of new benchmarks and a lack of maintenance for the other benchmarks. So in our paper, instead of trying to answer the question which benchmarks should be used, we try to answer the negation, which benchmarks should not be used, and the motivation behind using the negation is primarily to avoid setting up specific benchmarks to be gamed. Also, it allows for new and innovative benchmarks to be used and gain traction, and it encourages benchmarks falling under the question to be improved. Overall, we think that it could help in raising the floor of benchmark quality. We present a list of 7 criteria for when to deprecate benchmarks. Here you could see some examples. Basically, we provide a short description as well as some benchmarks that are facing similar issues. We can take high memorization as an example. So it occurs when models memorize benchmark data, either due to a leakage or contamination, and in that case, their performance no longer reflects true generalization with respect to the measured capabilities. In our proposed framework, we first have the assessment stage, and we raise the question, when should we deprecate? And this non-exhaustive list of criteria provide some potential answers. So we differentiate between full, partial, and mixed deprecation, depending on whether we could update certain components of that benchmark in order to still make it useful for a particular usage context. So when we discuss things such as contamination or statistical bias, it is possible to apply partial deprecation because we can just eliminate some data points without replacing the entire benchmark. But in certain cases, it's more problematic. So for example, when we determine that a task is obsolete, or in cases when there are certain validated assumptions on which the benchmark is based, it could be more problematic because these criteria apply to the entire benchmark, and in that case, we would have to implement full deprecation. Our deprecation framework has 3 stages: assessment, reporting, and notification. So in a fictional example for the assessment stage, the EU AI office could periodically review benchmarks for measuring biological capabilities of frontier models, and then based on it, it could compile a deprecation list. In the reporting stage, the governance actor would need to provide a justification for deprecating a particular benchmark, and the report might also include particular timelines for when to deprecate it, and the appeals process in case the benchmark developer decides to appeal. Finally, in the notification stage, a governance actor would have to inform stakeholders and discourage use of deprecated benchmark for cases such as academic publication, product testing, or model auditing. And here's a sample deprecation report, just to give you an example of what it could look like. Note that the deprecation details are fictional, but the mentioned flaws in the selected benchmarks are real, documented in the literature. Among other things, the report could include a justification for deprecating a particular benchmark. It could also propose alternative benchmarks that could replace it, as well as a deprecation timeline. In terms of more general conclusions, we believe that the proposed deprecation process could help mitigating cherry-picking and safety washing of model performance. It could also mitigate barriers to entry by new benchmarks and also degradation of widely used benchmarks. If we had to discuss some actionable recommendations that I haven't covered before, I would highlight the need to establish version control for benchmarks, some kind of versioning system, perhaps similar to a DOI, a digital object identifier that's used for academic papers, having some kind of unique code that could help in tracking these benchmarks throughout their retirement or when upgrading them. And then a second recommendation, and this one is for the benchmark developer, would be to have a deprecation plan when creating a benchmark and establishing a point of contact. Sometimes the funding dries up and then the benchmark is no longer maintained and it's unclear who to contact when it comes to making these important decisions, such as upgrading certain components or deprecating the entire benchmark. And if you're interested in more low-level details, here's the QR code to the full paper. Hey everyone, I'm Rokas. I'm here to present our...
Hi everyone, I'm happy to present my work on deep hierarchical learning with nested subspace networks, co-authored together with my supervisor Michaela Vandersharm. The primary premise of this paper is that we want to have architectures, neural network architectures, that can trade off two things. On the one side, performance, that means how good a model is, and on the other side, compute, which means how fast the model is. Typically, it's the case that the smaller the model, the faster it is to run, but then simultaneously, the worse it is. And on the other hand, big companies like OpenAI are building large models, which are very, very good. They're very expensive, but then simultaneously, they're very expensive. So the question this paper asks is, how can we have an architecture where you can have a single model and you could trade off these two properties, compute and performance, so your model could shrink when it needs to become smaller or expand when it needs to become larger, thereby becoming either more performative and expensive or cheaper and faster, but worse. And so there are three primary properties such a model should have. The first is we should be able to instantly adapt it at test time. So if you're, for example, talking with a language model or you're developing a vision model, you want to be able to just immediately, without any sort of fine-tuning, post-processing, or anything else, adapt the size of the model. The second thing is we want this model to be, or framework to be generally post-hoc applicable to a lot of pre-trained foundation models. And the reason for this is that a lot of the big models today that we care about are language models, and they go through massive, massive fine-tuning and pre-training. So there are these, multi-billion parameter models that are very expensive to reproduce from scratch. So any technique that makes a model smaller or larger must be able to be applied on all of these specific, more expensive, already pre-trained systems. And then three is we wanted to have granularity, meaning that we want to have a smooth continuum of points on this compute performance frontier. So we want to choose, for instance, how much specifically smaller or larger such a model should get ourselves. So in this paper, we propose an architecture to do that called nested subspace networks. The primary mechanism how we do that is the following, that if you typically have a multi-layer perceptron, you just have a weight matrix. We know that we can adapt typically this weight matrix by adding a LoRa adapter. In our specific case, we completely replace trainable weights with what we call rank trainable layers. So instead of learning a single model, we decompose these linear layers into rank trainable layers, and we formulate a loss function to encourage interpolation across a set of different ranks at inference time. So what that means is that when you're looking at the model, you can decide what rank of your model you want to have, and then that rank modulates or decides how big the model is, but also how expressive or non-expressive that model is. So fundamentally, this is about a new architecture on the weights of a network that allow you to trade off performance and compute by changing the ranks of the layer. Just kind of to make sure that we're on the same page, so the way we introduced this idea of a nested subspace network, and the idea is that instead of having a linear layer W, you have a decomposition of the linear layer into two weight matrices B and A. When you multiply them together, you get back the weight matrix, which is original, and then the rank in the middle controls the depth of your specific performance. So we specifically design a training strategy that allows this model to generalize across a lot of different settings. And we can actually show the visualized contributions of different ranks because we're training them individually. So the primary idea here is that we formulate a training objective where each rank, such as rank 1, 2, 4, 8, 100, etc., within the weight matrix, contributes a loss to the training objective. And we formulate an objective that specifically upscales or downscales them based on their relative contribution. And we find that what ends up happening is that the contribution of the rank is always the highest if the rank is the highest, and it's the lowest if the rank is the lowest. And here we visualize the log variance, all to say that there's a way to interpret what we're doing as an emergent phenomenon in terms of the impact of each rank on the performance of the model. We show and compare our model to specific different base layers with different MLPs. And the primary thing we find is that we can actually use one specific model, train it only once, and then at test time, adapt that model to have different sizes. And when we match it to a specific multi-layer perceptron for each parameter budget, we find that our model does equally well. So the main takeaway here is that if you wanted to train 30 different models of different sizes, now you don't need to train 30 different models of different sizes. You can train one model, and we show that we actually, on a parameter budget level, match the 30 different models. So that means that instead of training a smaller and a larger model, you train it once, at test time you match it. So that's a very useful property to have. Now, one of the things we talked about is that you need to apply it to pre-trained foundation models. I'm not going to get into the details of this too much, but the primary takeaway is that we show how to do that. So you know that language models are really big transformer architectures. So if you take a big transformer, here we visualized a gamma 2B model. What we basically do is we loop over all of the layers in the language model. We take out the linear layers, replace them with our rank adaptive layers. And what ended up happening is we are basically converting a full language model, which was fully functional before, into a rank adaptive language model. So now any language model can suddenly shrink or decrease or increase in size with the procedure we've introduced. So that means that this technique applies not only to some sort of like new networks, but we can take these very, very expensive pre-trained models, replace the linear layers with rank adaptive layers, and have a single model that increases or decreases in size. And we showed that actually this works in practice very, very well. So we test a language model on some specific tasks, and we see that, for example, on a task for reasoning in language models, we get a 50% floating point operation reduction. So it's 50% cheaper to run the same language model with only a 5 percentage point accuracy loss on these logical reasoning tasks. So in other words, we see this really, really, really smooth frontier where we now have a single model and we can, at test time, go and change these parameters bit by bit. And we see that it's becoming cheaper and cheaper to run the model, but the model becomes less and less expressive. And we do this with a bunch of models, and we consistently find the same behavior. So the big summary of the contributions, and I encourage you to look at the paper if this is something that you're interested in, is first of all, we introduced and formalized a new architecture, which we called nested subspace networks. The fundamental idea of nested subspace networks is that instead of having a single model, you can now have a whole hierarchy of models, and you can almost pick which submodel you want to be using. We show that you can learn these different submodels with the training objective we introduce. It's actually not trivial to learn this because simple training objectives don't allow you to learn many multiple submodels. We show some really nice performance curves, both theoretically and empirically, meaning that once you take a big model and you now adapt it so that it would actually have multiple submodels, what ends up happening is that you can pick different submodels of different sizes you haven't even trained for before. And that means you can generalize to models of different sizes, which is extremely useful. We show that you can adapt this flexibly to large pre-trained networks, and we show why and how and when it works, what happens with the network weights, etc. So fundamentally, we see this as a really important paradigm in how we construct language models, and it can enable us to have a single model that is adaptable at test time to have different performance compute budgets. Thanks so much for listening. Hi, everyone. Thanks for joining. So today I'm presenting the work Visualizing Token Importance for Black Box Language Models, co-authored together with my supervisor, Mihailo Vandershar. And in this paper, we want to understand or answer the question, how does the answers of a language model depend on the information it gets? And specifically, the information it gets is the strings of text, and we also can call them tokens. So tokens are subword units or actual words. And we're interested in how much emphasis does the language model place on each specific word. Now, this is very important because it helps us to audit the behavior of language models. If you want to audit language models, like it's clearly very important because if, let's say, we're using language models in legal settings or medical settings, we're asking for medical advice, we want to ensure that, the model is providing good, reliable advice. If, for example, it is looking at information that is completely irrelevant, for example, some sort of context that has no information or impact on the medical treatment, we would like to know that. We would like to see that, okay, the language model is spending a lot of attention and taking a lot of information from completely irrelevant pieces of information, maybe that's not good. Or if it's giving some sort of legal advice, because people are deploying these in legal settings, we want to ensure that the information it's looking at is also important, reliable. So auditing these kinds of language models becomes very, very important. But it turns out it's very not trivial. It's hard to do that. And the reason why it's hard to do that is because a lot of these really good models that are state of the art are black box. Black box meaning we don't have access to them. We don't have access to the architecture, to the weights. And so we cannot just go into the model and probe it. We have to just rely on the inputs and the outputs. And so then the question is, if you are working with such a model, which is highly performant, state of the art, you're using it in high stakes settings, such as medicine or legal settings, how can you know what model whether the model is safe? Now, here's just one motivating example. Is suppose that you're looking at this is a toy example I created just to make that point home, that suppose you're looking at a setup where there is a legal advice being given, and there's some information such as John Doe, so like name and surname, is accused of murder. So in this specific example, we want to know how much the model is paying attention to each specific word. So for example, we would like to make sure that the model is paying a lot of attention to the fact that there was murder going on. But if we change the name from John Doe to like an unknown other female name or an unknown maybe African American name or anything like that, the name itself, we hope, wouldn't matter too much in the sense that just because a specific person's name is given in the way it is, it shouldn't impact the kinds of recommendations it gets. So if my recommendation or sentence for a specific crime depends on my name, that's clearly bad behavior. We'd like to capture that. And the way to do that is to almost highlight and say, hey, look, this information is the most important. So that's what we want to do. Now, if you think about what this means in practice, then like if you formalize it a bit more, you want to understand token level sensitivity or word level sensitivity. And there's a definition used in statistics and machine learning. We don't need to get into the details of it, but the idea is that you want to understand how the whole output would change if you were to change the input just a bit. Now, the problem is that we don't have access to these models. We cannot compute this in any form, actually. And we want to understand how the output would change, not for just a single response of a language model, but crucially for all the possible responses it could give. And here's the reason why this matters. So suppose I give some medical information and I ask for a diagnosis. If I ask for the diagnosis twice in different circumstances, I will get two different answers. And the reason why I will get two different answers is because language models sample from a probability distribution, which means their answers are going to be different each time. So we cannot just, for example, change the name once, then change the name twice, compare the different answers, and say, oh, I see that the recommendation now differs when I change the name. And the reason you cannot do that is because maybe the recommendations would have changed anyway, because each time they're different anyway. So the idea is we want to understand how the model's all possible outputs or all possible answers it's giving would change, and how they depend on affect the entire distribution of responses, how they depend on each token, and how to evaluate that specifically well. And so we formulate this in the context of a hypothesis testing procedure from frequentist statistics. The main idea, which we invite you to look at the paper to get a bit more details, is we formulate this as a hypothesis testing procedure in the following sense, that if you change or perturb a specific token, does the output distribution change or not? So it's a kind of a null hypothesis versus alternative hypothesis. And you can sample Monte Carlo many, many times, or like some sort of like number of times to get a sufficiently good statistical estimate. And once you sample sufficiently times, by perturbing the token with some sort of nearest neighbors in embedding space, you can obtain a distribution of answers, compute the variability with respect to the null distribution, and obtain an effect size, which we can visualize. So if you didn't get that fully, that's completely fine. But the primary idea is that employing the tools of frequentist hypothesis testing can enable us to understand and visualize these specific black box models and their token dependence, even on a token level. So here are some examples that we've actually done, and we show that you can use a GPT-4 model and still obtain these specific visualizations. So here's an example in a legal audit. So suppose the following setup, where a technology company uses an AI-powered system to analyze legal contracts, and they want to understand is the language model maybe looking at the wrong information. So the company cannot rely on black box LLMs, and so they need more transparency, and they use this technique. And what ends up happening is that we see which tokens tend to be the most important for the language model. So we can see that for this specific audit procedure, the model looks a lot, or their results change a lot based on the words of revolutionary AI and the fact that there's California law, but it doesn't, for example, impact or change a lot by for example, the number of the money involved, or for example, whether the payment was for 3 months or longer. So this gives immediate insights into what information most impacts the legal recommendation. And here's another example in clinical support. So suppose the goal of this language model is to provide specific information about what to do for this patient. And after this, we can use this method that we propose in the paper to extract what are the 5 most important variables that if you change them, suddenly the whole model changes as well. And so we see that, for example, these specific 5 words have the highest impact on changing the whole distribution of the kinds of recommendations the language model gets. And that's very important because the doctor can now look and say, okay, well, we clearly see that the model shouldn't change its response on the basis of this or that token. So the primary takeaway is that we identify limitations within this paper on how currently language model auditing is performed. We introduce a new mechanism to audit language models, and we specifically make the claim that you need to audit their distributions. We develop a concrete procedure to do this and enable that procedure via statistical hypothesis testing from frequentist statistics. We build this algorithm and we validate this behavior for a bunch of language models in a bunch of different settings. And we have a very clear practical tool that people who do wish to analyze their specific language models can employ in order to see which specific tokens or words impact the kinds of answers the language model receives the most. Good. Thanks for watching.
In this work, we present highly accurate, cost-effective, and robust human-centric vision models trained solely on high-fidelity synthetic data. Our approach provides accurate, robust, human-centric dense prediction models trained on small yet high-fidelity synthetic data with low training and inference costs. Particularly, we show that we can achieve highly accurate results on human-centric dense prediction tasks of soft foreground segmentation, depth estimation, and surface normal prediction. In the literature, there are different approaches to train models that generalize to diverse scenarios. Big Transfer leverages a massive dataset of 300 million images with noisy labels for pre-training, providing a strong backbone for various classification tasks. For generalizable depth estimation, Depth Anything v2 leverages the giant version of Dino v2, first training on 600,000 synthetic images with perfect depth annotations, then generating pseudo-ground truth for 62 million diverse images to train student models. Depth Pro, in contrast, first trains a custom DPT model on a mix of real and synthetic datasets. To enhance fine details, it continues training on high-resolution synthetic data with perfect annotations. In another work, Sapiens focuses on human-centric vision tasks and pre-trains its backbone on 300 million real images of people using self-supervised learning. The pre-trained model then initializes weights for various downstream tasks, such as depth and normal prediction fine-tuned with synthetic data. While all these approaches show promising accuracy and generalization, they typically require very large models and expensive training. In this work, we take a simpler approach of training on a diverse, high-fidelity synthetic dataset that generalizes to real human-centric scenarios. We show that training on a small yet high-fidelity dataset is enough to achieve very competitive accuracy. Our models require only a fraction of the cost of training and inference when compared with large foundational models of similar accuracy. To train our models, we exclusively use synthetic data, generated through an existing pipeline that creates realistic, human-centric datasets along with precise ground truth annotations. In this work, we extend the use of this high-quality synthetic data to dense prediction tasks, where both realism and annotation quality are more critical, and for which annotations on real data are often impossible. We train all three models for depth estimation, surface normal estimation, and soft foreground segmentation on a single training dataset of 300,000 images. The images cover faces, upper body, and full body scenarios equally. We designed this dataset such that it is diverse in terms of poses, environments, lighting, and appearances, and not tailored to any specific evaluation set. Our models are built on top of Dense Prediction Transformer, or DPT. We first resize the input image and pass it to a VIT encoder for a fixed time encoder inference. Similar to a unit, we use a convolutional decoder with 4 blocks in which each block is connected to the encoder through skip connections. To enable inference on any input image resolution, we use a simple convolutional model called resizer. It injects image features into decoder blocks, allowing the decoder to reason about image features at input resolution. We use the same architecture for soft foreground segmentation, depth estimation, and surface normal prediction. Since we use the same architecture design and same training dataset across all three tasks, it is feasible to extend the model into a multitask one by adding decoder heads. This is computationally advantageous over running 3 separate models when all 3 output modalities are needed. Our human-centric dense prediction models deliver high-quality results that reliably capture a wide range of human characteristics, handle diverse lighting conditions, and preserve fine details like hair strands and subtle facial features. This demonstrates our model's robustness and ability to handle complex real-world scenarios with high accuracy. Here we compare our multitask dense prediction results with the existing SOTA models Sapiens 2B. We show that not only our model produces highly accurate predictions with fine details, it runs orders of magnitude faster than competing methods. Our relative depth estimation model generates a 2.5D representation from a single image, enabling 3D point cloud creation and novel viewpoint rendering while preserving complex depth relationships and object proportions. Our soft foreground segmentation model enables precise subject extraction, preserving fine details for high-quality background replacement in applications like video conferencing. Another application of our model is relighting from surface normals. By predicting accurate surface normal maps, we can re-render images under novel lighting conditions, creating shading and ambient effects that lead to a visually plausible relighting result.
Hello, my name is Kamilė Stankevičiūtė, and today I'm going to talk about PhantomWiki, a paper that has appeared in International Conference on Machine Learning earlier this year, and it is about generating on-demand data sets to evaluate reasoning and retrieval capabilities of large language models. Quality data and benchmarks are essential to understanding and developing LLM capabilities. However, benchmarks are very complicated. For example, it might be hard to isolate various model skills like reasoning about a question from scratch and retrieving the relevant information to answer the question from just regurgitating a memorized correct answer that exists out there in the internet. Another challenge is the possibility of overfitting. If an LLM developer is able to run an experiment many times, perhaps varying various hyperparameters or other settings, they might be incentivized to report the best outlier result and then not report any of the failed experiments. As a result, this inflates the performance metrics and makes the model look better than it actually is. And then the third challenge is that it's ultimately difficult and expensive to curate benchmarks, like gathering never-before-seen data and collecting human labels, especially if the questions are deliberately intended to be hard for the language model to answer. And also, once the dataset is released, it ultimately can end up in the training dataset of the next iteration of large language models. So any dataset that has been curated at great time and monetary cost ultimately becomes outdated and not suitable for fair evaluation. So we need a new kind of question answering dataset, a benchmark that essentially never appears in the training data because it's unique every time, a benchmark that is vast but at the same time inexpensive to generate, so it doesn't involve any time or human cost, a benchmark that can have verifiable answers also without human input or labels. And this is especially important because many current LLM-based synthetic data generators cannot actually guarantee correctness. So if you want to guarantee answers, that would be a great benefit. And we also want a benchmark that is controllable in difficulty levels and structure, so then we can actually isolate which skills are LLMs good at and which skills are they not good at yet. So for example, reasoning and retrieval, but you could also imagine like different types of reasoning questions or different like settings or situations where like reasoning fails. So PhantomWiki construction happens in 4 steps, which is to generate the universe, generate the Wikipedia pages, and then generating question-answer pairs. I'll walk through these steps next. So the first step is to generate a universe. So it's pretty straightforward. You pick the size of the number of individuals you want to include, and then for each individual you attribute some properties like names, dates of birth, hobbies, and then you generate relationships like family tree, friendship network, and such. And this is very extensible. You could imagine like including like also different events like rolling out of history and not just like a static snapshot of a particular universe. And then we also at the same time we store it in a special format, which is a logic programming database we'll need later. And logic programming database is represented as a set of rules that are kind of generic to any type of universe. So here we describe, let's say, how does the relationship of a mother work? So if for Y to be a mother of X, Y has to be a parent of X, and she has to be female. But you can make like more and more complicated rules as you go. And then you have facts specific to the universe. So that's where you kind of generate like your unique instances. Next, you convert these simple facts into Wikipedia-like articles. So they're Wikipedia-like, but they're pretty simplistic, which we see as an advantage because then we know that any answers are kind of not confounded by the complexity of the language because it's pretty straightforward. You could imagine like augmenting it with an LLM, but then it's hard to guarantee consistency as we observed in our experiments. Then we generate questions, and for this we use another old school NLP and like computer science tool, which is context-free grammars. So those kind of work by taking a non-terminal on the left and using the rule like to transform it to the output of the right. Some of them have like several options. So running through an example, we kind of start from the starting point and then we kind of sample the kind of placeholders until we get like a full question template, which looks like this. And then we transform this template into an actual question. So if the blue square corresponded to relation name, then we kind of pick a certain relation instance. And then we get like a question such as who's the mother of the uncle of the person whose occupation is plumber. We could also sample a different question and get like another type of question. So you could imagine like this could conceivably have many templates, and each of those templates could have its own many versions of questions. So those are very hard. Those construct a data set for which is very hard to prepare because there's like could be unique combination of questions at any point in time. And then we use that Prolog database that I mentioned earlier. So Prolog is one of the logic programming languages. And they're like finding a ground truth answers just corresponds to running a Prolog query and just getting the corresponding answers. Sometimes you could have multiple ground truth answers as well. So we evaluated in 3 settings. So in context, where it's straightforward, you just paste all the articles in the chat window and then just see what the model answers. We can use a retriever, which just picks which articles it thinks could be relevant to the question. And then we have an agentic setting where the model can request its preferred articles that it wants to read. And then we evaluate reasoning. So this we can isolate by just increasing the number of reasoning steps while keeping the universe size fixed. And then we see that the model kind of performance drops pretty rapidly. So when the question has only 1 step, so just reading from the article, then the models can still manage. But then when it kind of the question becomes longer and more complicated, kind of the models give up or forget something or like make the wrong number of iterations through the relationship. So for example, if someone is asked for the grandfather, then they might skip more generations or fewer generations and make like mistakes like this. And then we also evaluate retrieval. So if we make the universe very large, while keeping the reasoning difficulty similar, we also see that the models struggle with answering questions. And here RAG performs a bit worse than agentic, and that's probably because RAG doesn't have like this reasoning ability to retrieve the relevant articles in the first place. So that's what might be happening. And then the agentic kind of performs a bit better because it can reason about which articles it needs first. But it's still like not very, like there's still a ways to go for those models to improve. So in that sense, this makes like PhantomWiki quite a beneficial data set because it is challenging. So it creates like a fair evaluation, and it also creates like a frontier for where the models can improve. The data set is factually consistent. We can guarantee that the questions will have the correct answers. And the LLMs have no prior knowledge of the data set usually and must rely on internal skills. And it's very cheap to generate, and no LLMs or humans are harmed in the dataset generation process because it's all just fully programmatic. Thank you so much. This has been a work of a wonderful team from Cornell University and University of Cambridge. And if you'd like to check out the paper, here's the link to the archive and the GitHub repository. And thank you so much again.
Hello, everyone. My name is Gedas Bertasius. I'm an assistant professor at University of North Carolina at Chapel Hill, and today I'm going to talk about our recent work called BIMBA, Selective-Scan Compression for Long-Range Video Question Answering, which is a paper that we presented at CVPR 2025 last summer. And this was a joint effort with my PhD student, Mohammed Al-Islam, and also our collaborators from Meta AI, Tushar Nagarajan, Huyu Wang, and Lorenzo Torsani. So we're in a very exciting era for video understanding. Now with modern vision language models, we can solve a lot of highly complex video understanding problems. However, if we dive into even more complex long-range video analysis problems, which is lately what my group at UNC have been focusing on, we see that even the most powerful models still struggle with these problems. So take this example, a 30-minute video about the best fighters in this popular TV show called Game of Thrones. And here the question is, what does Jon Snow use to fight with Ramsay Bolton? So it's a challenging question that requires localizing the characters, finding the precise scene in a long video where the relevant moment is happening, and also identifying relevant objects. And so here's, for example, a human watching this video and trying to answer this question. So initially, they will try to find the moment where this fight between Jon Snow and Ramsay Bolton is happening. And so here's a moment, and now they might stop and watch this particular video segment for maybe 20 or 30 seconds to try to find what is the answer to this question. And here we already see that Jon Snow is picking up the shield, and so this is our correct answer. But when we prompt a powerful model like Gemini with the same question, we see that it incorrectly answers sword. And so this highlights a significant gap between the current model's ability to reason over long-form video with the human abilities to do this sort of complex long video analysis. And in my view, there are two main technical challenges for this problem. So first, the sheer scale of a long video input. So a 60-minute video sampled 1 frame per second results in more than 1 million tokens. And so this is far more than most existing vision language frameworks, especially those based on transformers, can handle efficiently, especially in the open source community. And the second challenge is that a lot of these long videos contain vast amounts of irrelevant content. And so finding this critical information needed to answer a question is akin to these needle in the haystack kind of problems, which is notoriously difficult for existing models, especially in the multimodal domain. So we propose to address this issue by leveraging these new kinds of structured state space models, also known as S4. So as a quick overview, these S4 models, they're essentially a recurrent kind of model like LSTM or RNN. And the key property of this S4 model is that it has a linear computational cost with respect to its sequence length. And so this is unlike the self-attention, which, as you all probably know, has a quadratic cost, which makes it a lot of times prohibitively costly to apply it on long input sequences. And so this makes S4 a lot more efficient for long sequence processing. And in our prior work with my student Mohammed, we already successfully leveraged these S4 operators for tasks like long movie clip classification and scene detection. And in this work, we're going to be building on these successes. But the original S4 models have one critical limitation. So they really struggle with tasks that require selective focus on specific input. So here I'm showing this a toy problem called selective copying, where basically, and this is only in the language domain, where the task is to extract all the nouns from a sentence. It's extremely easy to solve this task for transformers because of their attention mechanism is dynamic and data dependent. But a standard S4 model performs very poorly because it's essentially time invariant. So these parameters that I'm showing, A, B, and C, they're static. They're essentially the same for every token. And this limits the model's expressivity. And so essentially we have this trade-off where with transformers, we have these very powerful data-dependent dynamic representations, but at quadratic cost. And with these S4 models, we have weaker representations, but a linear cost with respect to input sequence length. And so recently, a new approach tried to combine the best of both worlds. And so this brings us to this recently introduced BIMBA model, which utilizes a selective-scan algorithm. And the key innovation in BIMBA is making these parameters B and C essentially input dependent. So now these matrices B and C that I'm showing here are going to be dynamically generated based on the input token. And this will allow the model to selectively choose what information to retain and which information to ignore, achieving this data-dependent representation while still maintaining linear time efficiency. And the key question that we want to answer here is, can we leverage this selective scan algorithm to efficiently select relevant information from a long video needed to answer some complex question about that video? And so to do this, we introduced this model called BIMBA for bidirectional interleaved Mamba for better answers. At a high level, BIMBA is an efficient architecture that compresses long videos into a short, information-rich sequence of tokens. It consists of standard image encoder, our novel spatiotemporal token selector, and then a pretty standard LLM decoder. And the core innovation here is the spatiotemporal token selector, which uses a selective scan algorithm. And so because it operates with linear complexity, it's very efficient. So essentially what this means is that we can compress over 100,000 input tokens down to just about 6,000 tokens for efficient processing by a LLM. And in contrast, standard self-attention, it often runs out of GPU memory even just beyond 10,000 tokens. And the spatiotemporal token selector that we propose, it's also a plug-and-play module. So it's very easy to integrate into any existing vision language model. So let's dive a little bit deeper into how it works. So we implement this selector using the selective scan algorithm, which I previously discussed. Essentially to efficiently model these long-range spatiotemporal dependencies and only select the most relevant tokens needed for long video analysis. And so we achieved this compression by introducing a small set of learnable visual queries, which I'm showing here in yellow, and then jointly modeling them with the raw video tokens, where I'm showing here in blue. So here V1, V2, V3, V4, these are different video frames, and then vertically, these are just different spatial tokens for those frames. And so the standard approach in prior works is typically to append these yellow vision query tokens at the end of a sequence. However, we found that this introduces a positional bias where now the queries are disproportionately influenced only by the tokens at the very end of the video. So instead, we propose to interleave the visual queries at equal intervals throughout the spatiotemporal tokens, as I'm showing here. And this mitigates the positional bias and also allows the queries to gather information more uniformly across the entire video sequence. And then finally, we also use this bidirectional selective scan mechanism, which I'm showing here on the right. And we found this approach to be a lot more effective at capturing complex spatiotemporal structures inherent in video compared to a standard unidirectional scan, which was designed for 1D sequences. So next we evaluate this BIMBA model on the recently proposed ego schema dataset that's specifically designed for this complex long video analysis. Ego schema contains 5,000 videos with multiple choice question answer pairs, focusing on long video analysis. And here we analyze the performance of different models as a function of a number of spatiotemporal input tokens. So on the y-axis we have accuracy, on the x-axis we have a number of tokens. And in our comparisons, we include our BIMBA model as well as other baselines like perceiver, standard self-attention, a relatively simple pooling baseline, and a vanilla model without any compression. And so the key takeaway from these results is that, so first we see that self-attention runs out of GPU memory beyond 10,000 tokens. And in contrast, BIMBA, demonstrated by this blue curve, consistently outperforms all other compression methods, and its performance monotonically increases as more tokens are added, scaling up to over 100,000 tokens. So this demonstrates the effectiveness of this Selective-Scan compression module. Next, we also compared BIMBA with state-of-the-art vision language models across 7 diverse video question answering benchmarks. And as you can see in the bottom row here, BIMBA achieved state-of-the-art performance across all of these 7 benchmarks, while also being more efficient than many of these state-of-the-art models at long video processing. And then we're also very proud of our results on the recent Ego Schema Challenge, which was held at CVPR 2025, where our improved version of BIMBA achieved 81% accuracy, winning the first place, and also for the first time surpassing the human baseline of 77% on this challenging benchmark. And qualitatively, you can use our BIMBA model to take an hour-long video, for example, a full documentary, ask a highly specific question that would typically require you to rewatch the entire video, and then BIMBA can provide an accurate answer in about 15 to 30 seconds. So that's incredibly useful for quickly extracting information from vast amounts of video data. And furthermore, BIMBA isn't limited to just single question answering. It can also engage in complex dialogue about the video content. So it can handle a wide range of queries from detailed descriptions and action recognition to inferring high-level goals and even explaining nuanced concepts like humor. So to summarize, one key takeaway is that long video question answering is still challenging even for the most powerful models like Gemini, mainly due to this a large number of video tokens and the need to do precise temporal localization. And then our proposed BIMBA model can use this novel Selective-Scan compression algorithm to handle sequences with more than 100,000 tokens efficiently and effectively. And then empirically, we saw that this BIMBA model achieved state-of-the-art results on multiple video question answering benchmarks, and also it surpasses human performance on this challenging ego schema benchmark. And so with that, thank you very much for your time and attention, and please check out our project page for more details, where we also have released all of our code and pre-trained models. Thank you.
Hello everybody, I'm Povilas. The presentation is measuring statistical dependence via characteristic function IPM. So the authors of this paper is me, Shubham Junėja, Lukas Kuzma, and Virginijus Marcinkevičius. And this paper is affiliated by Neurotechnology, Vytautas Magnus University and Vilnius University. So it has 3 parts. First, we discuss statistical dependence and UFDM, which is our contribution. Afterwards, we discuss experiments with this measure and also discuss potential applications. And this presentation is about our recently published paper, which is in this slide. So first about statistical dependence. Let's say we have 2 random vectors of arbitrary dimensions, and we want to somehow measure how they are statistically dependent. So we define some functional which is non-negative, which should be 0 if and only if there is statistical independence between x and I, and also increasing values of this functional d should correspond to the increasing statistical relatedness of x and I. So probably one of most popular examples of such a measure is mutual information, which is defined in the top of the slide. However, in practice, it is hard to estimate mutual information using this definition, because you need to fit densities and so on. Because of this, usually other representations are used, like variational representation, provided also in this slide, where you maximize this quantity by searching neural network parameters theta, which does that. So this approach is called 9. However, mutual information is not convenient in all applications. Because of this, other statistical dependence measures were proposed in literature, like distance correlation, HSIC, matrix-based entropy functional, and others. So, in order to define our measure, we need first to define two components. So, in context of estimation of statistical dependence, the integral probability matrix, or IPM, is a class of metrics between two probability distributions, joint probability distribution, product marginal probability distribution, which is defined for a function class phi. So you fix some function class and you calculate this suprema. So second component we will use is characteristic function. So basically it is Fourier transform of probability distribution. You have joint characteristic function and marginal characteristic functions, which are defined in this slide. Now we can proceed to the definition of our proposed measure UFDM. First we define delta, which is difference between joint characteristic function minus product marginal one, and we compute uniform norm of this quantity. So, because of this, it is a name, uniform Fourier dependence measure. Interestingly, that this measure returns not only the dependence value, but also parameters alpha, beta, which maximize delta, and also they can be interpreted in some scenarios. So, also we provide the code of this measure implementation, which was used in our paper, and you can download it and reproduce experiments and try to use in your research as well. So here we provide repository. Now about estimation of FDM. If we have IID sample of X and I, we use empirical characteristic functions to estimate UFDM by maximizing the provided quantity with respect to alpha and beta. However, in experiments we observe that random initialization of alpha and beta usually leads to very unstable estimates, especially in larger dimensions. So we came up with the idea to do first warm-up, like we calculate cross-covariance matrix, then we do SVD, or just calculate first leading singular pair of C, and initialize alpha and beta with this pair. Afterwards we have much more stable estimation. Now about some properties of UFDM. We can prove that it is 0 if and only if we have independence of X and I. Also we can prove that UFDM is an interval from 0 to 1. Also it is symmetric. Under full rank linear transformation, UFDM is invariant. Also it is invariant to data augmentation with any amount of coordinates of independent noise. So if you add any amount of coordinates to X, or to I, or to both, you have the same measure Xi. Also interestingly, when both x and I are zero mean Gaussian random vectors, the evaluation of this measure is equivalent to finding the first leading canonical correlation pair. Another theoretical result is concentration bound. Probably it is not optimal, but we proved that under second moment assumption, we can estimate this deviation between theoretical and empirical UFDM, and this deviation is bounded by the expression in the right side, which goes to zero when sample size n increases. Now we can go to the practical part of this research. The first experiment we conducted is permutation test. So we compared UFDM with distance correlation, xig, and matrix-based entropy functional with Gaussian kernels. The sigma were estimated using popular median heuristics, and we also investigated 16 distributions, 2 sample size n, and 3 dimensions using permutation tests. So we used 500 permutations per p-value, and for independent case we computed 500 p-values, and for dependent case experiments we computed 250 p-values. So in short, in the independent case, UFDM showed good type 1 error control, showed uniformity of p-values, and for dependent case it showed larger statistical power comparing to distance correlation, xig, and matrix-based entropy functional in some sparse geometric patterns. However, for the same sample sizes and increasing dimension, like dimension more than 50, statistical power rapidly declines, hinting that this measure probably is more data hungry to be efficient in permutation tests. Another experiment we conducted, it is supervised feature extraction, where we tried to find linear projections of the data, like in the second equation, and those projections were found by maximizing third equation. So we maximize dependence between projection and output variable and use those projections to logistic regression classifier and compare accuracies when those projections were calculated using different dependence measures. Our measure, distance correlation, xig, and MAF. We also added like hard baseline neighborhood component analysis, which is specifically a classification approach, and this task was classification tasks. So we compared 16 data sets. We had 160 method comparisons, and UFDM was statistically significantly better in 20 cases and statistically significantly worse in 13 cases. So it is like a useful complementary measure for probably not only for this task, but like for representation learning tasks. Now we can proceed to the third part of the presentation and discuss few other applications where those measures can be applied. First one is unbiased representation learning. So let's say we have the shape classification task. We need to classify two-class problem, the circles and triangles, and each data point has 2 attributes. The first one is color, and another one is like geometric shape attributes. And when we train the classifier, it can be that we found ourselves in the situation like in this slide. The classifier learned to classify the data based on color. So it learned biased representation, and it is undesirable. And authors of this research solved this problem in very simple way using dependence measure. So they add additional regularization term to the task, which is mutual information between representation and color variable. So after you minimize this loss, you have the representation which are independent of the color, and also they are efficient for classification. Another task where statistical dependence measures can be applied is bivariate causal inference. So let's say we have the sample of the data x and I, where either I is function from x plus some independent on x additive noise, or vice versa. So in theory you can prove that if the first model is true, then very unlikely that the second model is true, and similarly, if the second model is true, it is very unlikely that the first model is true. So the problem is related to the independence of input and noise. So the very simple illustration of this idea is provided in this slide. So in the first graph we see the model, and we see that noise is independent on the x, because for any x the distribution of noise it is the same. And in the other graph you can see that it is not the case. So using statistical dependence measure and statistical independence test, you can check whether direction is true, whether the x is cause or I is effect, or vice versa. So thank you for your attention, and if you have some questions, you may contact me, for example, by LinkedIn, and we can discuss.